Hello, this is Mr. Kenzie Factoring Review, completely factoring, and four-term polynomials. First thing we want to do with this, we want to look for a GCF. The GCF would be a 2, and then whatever the smallest exponent is. This is an x to the third, this is an x to the first, so it would be an x to the first. Now I'm going to take that 2x and divide each of these terms. So here we divide 2 divided by 2 is 1. Subtract the exponents. 3 minus 1 would be x squared. 32 divided by 2 would be 16. Don't forget it's a subtraction sign. And the x's simplify out. Now, we're left with this. This ends up being, after the GCF, a difference of perfect squares. We factor the x squared, so x and x. We factor the 16, so 4 and 4. The signs then are opposite. So we have plus and minus. So we factor that with GCF and then difference of perfect squares. We take a look at number 9. For number 9, we're going to look for a GCF. You always look for GCF first. And what's in common is an x. So I'm going to divide each of these terms by x. X cubed divided by x, we subtract the exponent. That becomes x squared. 7x squared divided by x, so plus 7, because 7 divided by 1. Subtract the exponents. 2 minus 1 would be x to the first. Here, we bring down the 10. The x's are the same. So now we're left with a trinomial guess and check factoring. So we have two sets of parentheses. We factor the first term, so we have x and x. Last sign is positive, so signs are the same. Take the middle sign. Factors of 10 that give us 7 would be 5 and 2. So once again, another factor, and we had GCF, but this time we had a trinomial guess and check. Number 10 is unique. There's nothing in common, and there's two terms. Both are perfect squares. I know x to the fourth is a perfect square because the exponent is even. So I'm going to put two sets of parentheses, x to the fourth, so it's x squared, 1 and 1. Signs are opposite. Now, we have two binomials. This one is non-factorable because it's a plus sign. Difference of perfect squares is the difference, so subtraction of two perfect squares. So I'm going to factor this as x minus 1 and x plus 1. I then have x squared plus 1 here for my first binomial. And I am left with these three binomials. So we actually had to factor difference of perfect squares twice. For number 11, this is a four-term polynomial that we're going to factor. Anytime you have four terms and you cannot combine any like terms, you're going to use factoring by grouping. So we're going to group these two, or pair them off. So here I have 12 and 3. Those are both divisible by 3. We then have x squared. So we have 3x squared, we're going to divide by each term. So when I do that, I am left with 12 divided by 3 is 4. 3 divided by 3 is 1. We subtract these exponents. That actually kind of just simplifies out, and we're left with just plus v. Now, if I'm doing this correctly, I should have the same binomial from the left to the right. The GCF here, all right, will be a 7 and a y to the first power. So I have 7y, which I'm going to be dividing both of these. 28 divided by 7 is 4u. 7 divided by 7 is 1. The y's simplify out. We are left with plus v. Those are the same. So because those are the same, I know I've done this correct. I'm going to group those two. So I have 4u plus v. And then I'm going to group these two individual terms to make another binomial. So I have 3x squared plus 7y. So that right there, once again, is factoring with grouping with four terms. Number 12. Number 12 and number 13 are very unique problems. All right, we have this one, so we're going to group these two. Can't combine them. Take the GCF. So the GCF is 1 and 5, so we're not going to factor out a number. But for our exponents, we take the smaller exponent. So that is going to be x squared. So I'm going to divide each of these terms by x squared. I'm left with x plus 5. The GCF here because they're both negative, we're going to factor out a negative. It's going to be -9. So we're going to factor out -9 from both of these. We're left with x plus 5. These two binomials are the same. So now what I'm going to do is I'm going to group those two. So I have x plus 5, factor out that common binomial, and group these two individual terms. This one ends up being a factoring by grouping, but then also factoring a difference of perfect squares. This is non-factorable, but this one is. So we have x plus 5. This is difference of perfect squares. I know that because it's two perfect squares separated by a subtraction sign. So I have x and x. The signs are opposite. And we have 3 and 3 because that's the perfect square of 9. Number 13, very similar to the last one. We have two binomials we're going to group together. Take the GCF of the first, so we have x squared. We're going to divide by x squared on both of these. So I'm left with x plus, these are the same, so simplify out, and that turns to 1. And then here, have a -4. So I'm going to divide each of these terms by -4. So we're left with x plus 1. We then group these two binomials and factor out that binomial. So I'm left with x plus 1. And then I'm going to group these two individual terms. So I have x squared minus 4. Just like the last one. We have difference of perfect squares here. So I'm just going to rewrite x plus 1. That can't be factored anymore. But this one can because it's perfect square, separated by a subtraction sign. So here I have x plus 2 and x minus 2. So we were able to factor that by grouping and then difference of perfect squares. So the last two, numbers 12 and 13, we're actually completely factoring. Thank you.